In today's seminar. Wrote some notes here. So it's an honor to introduce one of my dear colleagues, Dr. Robert Gregg, who I've known for many years. Dr. Gregg is an associate professor in the departments of robotics and electrical engineering and computer science at the University of Michigan. Before joining Michigan, he was an assistant professor in the departments of bioengineering and mechanical engineering at the University of Texas at Dallas. He is the founder and director of the Locomotor Control Systems Laboratory, and as you'll see today, he specializes in control of legged locomotion with applications in powered prosthetics, exoskeletons, and autonomous humanoid robots. And at least as on a personal note, he's arguably probably best known for his development of unified and continuous controllers for robot walking. He's received numerous prestigious awards for his robotics research, including the NIH Director's New Innovator Award. So without further ado, please join me in welcoming Dr. Robert Gregg.
Well, thank you so much, Bratislav, for the very nice introduction and the invitation to be here. It's very nice to see the campus and see good colleagues. So yeah, I guess I don't need to mention the topic of the talk. I'll just dive right into it. But first, I do want to, if I can get my slides to advance. There we go. First, I want to give a little shout out to the University of Michigan Department of Robotics. As of 2022, we have a bachelor's, master's, and PhD degrees in robotics, although the graduate programs have been around for about 8 years or so. So just a 4-hour drive away, so think about it. If you're ever looking for your next degree, we're always looking for bright and talented students. So first I want to preface my talk by discussing some of the challenges in amputee locomotion that my research aims to address. And so in particular, using conventional prosthetic legs, they're typically mechanically passive devices. Sometimes they have microprocessors to control variable damping, but they don't actively inject energy, they don't actively control motion, and because of that, individuals with low limb amputation tend to have difficulty with variable cadence walking, navigating ramps, stairs, sit to stand. Essentially, the greatest challenge is when you're doing positive work activities, because those devices don't contribute that, and so then you have to compensate with the intact joints, which then ends up risking overuse injuries that can lead to osteoarthritis, back pain, and other secondary issues. The hope is that powered prosthetic legs can restore normative gait biomechanics, and there is some evidence of this in the literature, but it does add substantial complexity through the use of sensors and actuators, and then of course the control and intelligence that bridges the two. And so that complexity has really held back the field. In fact, there's not a single commercialized powered knee and ankle prosthesis available. So you can't go out and buy one and use it. There are individual joints like powered knees and powered ankles. They don't work together, and they have their own limitations as well. So to kind of explain the complexity that we deal with, it's primarily in the area of control. And so typically we have this hierarchical control approach where we have a high-level control system that refers to the activity or the human intent. And so you can imagine, well, we have different potential walking speeds or cadences. There's different inclinations of the ground that you can be walking on. And there's more than just walking. There's stairs up and down. There's sitting and standing, and so you need to account for all these different possibilities. And then, assuming you know what the activity is at a given time, then you need a mid-level controller to determine the joint level behavior for that activity. And so, a common approach that's been adopted for over a decade is to use a finite state machine controller, almost like gain scheduling. And so you have these switching rules that will determine whether you're in one of these 5, or sometimes it's 4 phases of gait, and each one of those phases has its own distinct controller or control parameters. And not only do those parameters need to be tuned to every activity and every person, but also the switching rules between them as well. And so you have this explosion in complexity in the parameter space. You end up having more than 100 parameters in some cases for a multi-activity control system. And a good fraction of those are user dependent. So they need to be tuned by experts. And not just anyone, but people that thoroughly understand the technical development of these controllers. And so that makes them very difficult to deploy in clinical practice. Now, assuming we are using a finite state machine like we see here, let's say we're in the foot flap phase and you know what the parameters for stiffness maybe, or damping, or equilibrium angle. This would be what the so-called impedance controller. So trying to emulate a virtual spring and damper at the joints to give you a nice compliant interaction with both the user and the environment. Well, then the low-level controller would then calculate the torque from those parameters, which again will change from phase to phase or activity to activity. And so this is, as you can see, it's a very discretized way of controlling these devices, right? You discretize the gait cycle into multiple phases. You discretize activities into distinct tasks, as we see in that high-level bubble there. And so what my research has been doing over the past 10 years has been trying to go from this continuous paradigm, from this discrete paradigm to this continuous paradigm. And so we started looking at continuous phase, and so we were able to unify the gait cycle under a continuous nonlinear control law that is parameterized by something called a phase variable. And so we use a phase variable based on the residual thigh angle with respect to gravity. And you can think about for someone who's lost their leg above the knee, you still have intact hips in most cases that essentially acts as like the crank to the gait cycle, right? So the hips are what's cranking the gait cycle forward, and then we can measure that through an inertial measurement unit, which I'll talk about later, and then you can essentially map that to this, we call this clock or phase oscillator that tells you whether you're at 0% or somewhere between 0% and 100% of the gait cycle. And so that helps a lot with the individual gait. But then there's still this notion of discrete tasks. And so more recently, we've been working on continuous representations of the activity space, where you can imagine that you can walk at any real number for walking speed, or any reasonable real number for ground incline, and you want to be able to accommodate whatever wherever you are on this multidimensional activity space. So let's say this point might correspond to walking at 2.2 miles per hour, sorry, American, and 9.31 degrees, just arbitrary numbers, but the idea is that it's a continuous space. You can be anywhere on this three-dimensional space, and this could potentially represent like transitions from walking to stairs. It's just a cartoon, but it kind of gives the idea that if you take points in this multidimensional space, if you know what those points are, then you can, if you have a model, you can map those points to the desired joint kinematics or impedance or other objectives. And so let's get into this a little bit deeper. So the continuous phase variable idea, as I mentioned, we have to record the thigh angle somehow. And so we put an inertial measurement unit at the top of the knee hinge, which is more or less rigidly coupled to the residual limb. Of course, there's soft tissue and the fit of the socket will of course impact things, but the idea is that if this is attached to the residual limb, then this is measuring the residual limb angle with respect to gravity. And so if we're able to measure that, well then there's a lot going on here, but the important thing is to note that we have these kind of monotonic regions of the thigh trajectory during gait. And this is, by the way, true of walking, stair locomotion, ramp locomotion, even to some extent for sit to stand. And so the idea is that if we know which part of this trajectory we're in, then we can map these monotonic trajectories to a percentage of the gait cycle. And that's how we represent the clock coming from the user's residual limb angle. Now, we have these problematic areas where the trajectory is changing directions, and so then we use feed forward typically, or some other workaround, because then you lose uniqueness here. terms of mapping to gait phase. So here and here, we have to worry about using uniqueness, and so then we have, like I said, workarounds that we can use the feed forward term or whatnot. And so anyway, I did mention earlier that we were trying to avoid finite state machines, and it's kind of ironic that our solution ended up being a finite state machine, but it is different though in the sense that this is only for the phase variable, and these are not all unique things. It's more of like a supervisory system to make sure that we know which side of this piecewise monotonic trajectory we're on. But otherwise, there's two mappings. There's a mapping here and a mapping here. And so it's not like we have different controller for every single part of the state machine. And so here you can see that it's pretty robust to different ground inclinations. This is walking over different ramp angles. And you can see that the phase estimate is robust to those conditions without any adjustments to it. And so essentially this gives us the ability to accurately, to some degree, measure the user gait cycle phase. And that will allow us to synchronize the behavior to the user. And so in terms of the mid-level / low-level control, the idea that we embrace is a combination of position control and impedance control. And so the idea being that during stance phase, when we're interacting with the ground, we want compliance. We want it to be soft and comfortable. And so we use impedance control there. And so essentially we're rendering a virtual spring and a virtual damper. And those will be functions of the phase variable. So S is our calculated phase variable. And so there'll be functions of that variable. And we have ways to model what those values should be. We'll talk about that later. And during swing phase, we care more about foot positioning and also ground clearance. And so that's more of a position control objective. And so, and again, we'll have the desired trajectory as a function of phase, but now we're doing essentially PD control for the swing phase. And so we call this a hybrid kinematic impedance controller, or HKIC, and you can see that both parts of it are parameterized by the phase variable, and we'll make sure that the prosthetic leg is synchronized to the user. Now, in terms of the task, we consider multiple variations of walking. And so you can think of walking as a space of continuous variations, including speed and ground slope. And so we need to be able to model the behavior that we desire the leg to have across that continuous space. So as you move from walking to running, or from upslope to downslope, or vice versa, we want to be able to parameterize a model that will give us the desired biomimetic behavior of the leg, whether it's a biomimetic position trajectory for swing phase or a biomimetic impedance reference for stance phase. And so, first of all, though, we have to measure the task. You know, where in this two-dimensional space are we? And so we can do that using, again, the thigh IMU, and joint encoders can give us a very, very accurate measurement of walking speed. And then we also use a foot IMU to measure ground slope. Essentially, if we know when the foot is flat on the ground, then the orientation of the foot, which we get from the IMU, tells us the ground slope. Okay. So at mid-stance, every step, we can measure the ground slope. And so we can measure that with pretty good accuracy, which we'll talk about in a bit. Once we know what those variables are, then we use these models which we generated from able-bodied reference data. So the idea here being that if we can replicate normative gait biomechanics on the prosthetic leg, then that might enable more comfortable walking with the prosthetic leg with fewer compensations. That's the idea. And so we have a way of doing this, which you can check out in this paper here. But the idea is that we have these parameterized models for joint kinematics as a function of phase and incline angle and walking speed. And we also have a parameterized model of joint impedance. And here I'm only showing knee stiffness, but there's also damping and equilibrium angle as well. And these are all just generated from lots and lots of able-bodied data over various activities. So we have a dense sampling of the activity space to generate these models. And so here's a video that demonstrates some of the functionality. And so we're going to fast forward over this trial because it's kind of long. You can see the ground slope is changing for the treadmill here. There's also changes in walking speed as well. And the leg is adapting in real time. And these are our errors, root mean squared errors for the estimated incline angle and walking speed. And so they're all pretty manageable errors in the sense that you can't really tell the difference between a flat and level surface and a 0.6 degree surface. There's no way you can really tell that difference. And so it's almost imperceptible in terms of the error. And then in terms of, again, I mentioned that our goal is to restore normative gait biomechanics. And so one way to assess this is through joint kinetics, joint work, okay? So we're not directly controlling joint work, like that's not something that we have explicitly in our feedback loop. But if we're doing a good job of replicating the joint biomechanics from the able-bodied data, then we should be delivering the appropriate amount of joint work throughout the gait cycle as a function of incline or as a function of walking speed. And so what we see here is, in pink, is the able-bodied reference. And the general idea is that as you increase the ground inclination, you increase the work, or vice versa. If you're decreasing the ground incline, you decrease the work done. As this is intuitive. And you see that HKIC, the green curve, is our controller, and it's doing a pretty decent job of tracking the able-bodied reference there. FSMC is just a state-of-the-art finite state machine controller for reference, and it's also able to capture some of those features, but not as closely. And then over walking speed is a similar pattern. As you increase walking speed, you increase the joint work, and so so anyway, we see pretty good representation here of those joint work trends. So now that was walking. We also care about stairs as well, and so we have a similar approach where we have a kinematic model for the swing phase and the impedance model for the stance phase for stairs. Again, trained now on stair data. And you can see here's one of our participants able to do a step-over-step stair ascent, which can be challenging. But because it's delivering the appropriate amount of positive work, it becomes possible with relatively little compensation on the attack side. Now, so we have a walking controller and a stairs controller, but what about transitions between those activities, right? So we don't always stop at a staircase and then start again, right? Like, ideally, someone could just walk continuously from one activity to the next. And so we modeled those continuous activity transitions as a convex combination of the two steady-state controllers. Okay, so the idea is, in yellow here we see the steady-state stairs controller, and in blue we see the steady-state walking controller, and in red we see the transition from walking to stairs. Okay, and then in the shaded region is the convex hole between those two those two models, and we're able to then derive, again using able-bodied reference data, we're able to derive the rate at which you should be moving from one controller to the next. And so alpha here represents like the interpolation variable. So where are you between the two controllers in this convex combination? Should be between 0 and 1. And I guess we start at 1 for walking and we end at 0 for stairs. And so again, we've been able to model this by fitting the interpolation trajectory alpha to reference beta, and we end up with these models. Walk to stairs and stair to walk with the kinematic objective. And so here you can see experiments demonstrating the continuous gait. And we've also extended this recently to stair descent as well. So what we've done in summary here is we're reducing the dimensionality of the activity space from several distinct, discrete activity modes where now we're merging them into, let's say, one walking mode with two different variations over inclines and speeds. And then we also merge stairs into one model where we have variations in incline. And so again, the difference between stair ascent and stair descent is just the inclination or the step height of the stairs. Just like the difference between ramp ascent and ramp descent is just the incline of the ground. And we also can merge sitting and standing under one continuous mode as well. And so you can see here, I didn't really talk about the sit-to-stand controller, but that's also based on a phase variable, and it provides very useful synchronization to the user's intended sit-to-stand motions. And so, but now that begs the question of, we have these modes, how do we switch between them, right? When do we know when the right time is to switch? And so, I know that I said we have three modes, and it's true, we have three control models, but when it comes to classifying between them, we actually need to further differentiate between stair ascent and stair descent, because we need to anticipate the difference there. We can't just wait till you hit the staircase. It's too late by the time you hit the staircase with the stairs. Ramps, on the other hand, it's okay to be reactive, and so we essentially approach ramps not knowing a ramp's there until we hit it, and then during mid-stance we measure the ground incline, and then we adapt, and that's okay with a ramp. With stairs, foot placement is so critically important that we need to be able to know whether you're going up or down. And so we do separate those out in terms of the classification space, even though they're using the seating control model. And in order to anticipate stair ascent versus descent, we need more than just proprioception, essentially. We need environmental perception to be able to anticipate that early enough. And so we recently started using an ultrasonic sensor to give us, it just gives you one feature, distance to the nearest object. And if you know when to trust that measurement, which is part of the special, part of making this work is knowing when to trust it. Because you don't want to trust a measurement when it corresponds to, I don't know, the ground in front of you or the chair next to you. Like you need to know when to trust that measurement. So that's part of the challenge. But if you do know, then you can see a staircase as you're approaching it. And you can see, okay, that distance is getting shorter and shorter and shorter. That's a staircase. And combined with some other logic related to proprioception, we're able to then enable transitions between these modes. And in fact, using heuristic, very interpretable rules that we can coach people on. We can explain the rules in a way that gives them essentially volitional control over the transitions, which is distinct from a lot of the more common machine learning approaches that, while very, very promising, especially when trained on subject-specific data, they're not interpretable. And so when the misclassification happens, you don't know why, you don't know what to do differently next time, and oftentimes there's no way to recover from it without a manual intervention. Whereas if you have these kind of very simple heuristic transition rules that can be coached and understood, then you can learn how to make the transitions more reliable, more accurate, and also we've been able to add backup logic to correct early mistakes. So you got two chances at it. And that ended up being very, very useful. But to share, first I want to talk about how we validated this. And I wish I could share more details here, but we currently haven't filed the patent for this yet, but we are working on a paper. It's written. We're going to submit it for review soon. I can't wait to share it more broadly. But here's a quick preview of our validation, some of the results. So the idea is we wanted to validate this classification method in two scenarios. One is under a more comfortable self-paced scenario where you walk at whatever speed you're comfortable at, and we're also going to then equalize the number of intact side leading transitions versus prosthetic side leading transitions, because that also matters in the sense that most classification methods require one or the other. And so we wanted to enable both in a very, so that people don't have to think about their foot placement before they hit the stairs. They can just go wherever their feet end up landing. They can lead with the prosthetic side or the intact side. And so we assess both of those. And so we in this trial we're doing sit, stand, walking, stair ascent, and this as well as the reverse direction. And then another kind of unique assessment, we then evaluated a fast-paced or fatigued scenario. This is really important because as people fatigue, their gait patterns change in subtle ways. And all these data-driven classification methods that are out there in the literature, they're trained on more comfortable self-paced conditions. Whereas if you're out in the community walking for a long distance, maybe to catch a class or something, then suddenly you're fatigued, and then the classifier that you've trained on your non-fatigue data doesn't work anymore. And so we found this to be a very important assessment that's been kind of underutilized in the field. And so we had them do as many laps as they could until they couldn't keep up with a predetermined timing interval for each trial. And this involved ramps, sit to stand, stairs, all the activity modes. And then if for our very high performing participants who never tired out, we ended up adding weight to them and a weight vest after 90 minutes. Only one person actually needed this. Very impressive that they were able to get that far. But anyway, we'll talk about that later. So this shows the self-paced experiment. So this is all, again, this is all the automatic classification. And you can see on the TV screen as the leg recognizes the activity. And in terms of results, you can see here that we had, let's say, about 98.5% accuracy for the first participant and above 99% accuracy for the second participant. And we'll talk about the recovery rate later, but you can see that's 100%. So when there was a misclassification, they were able to recover from it 100% of the time without the researchers intervening. Okay. We'll talk about that in a second. This is the rapid-paced endurance experiment. Shown that, fast forward because kind of each lap is kind of lengthy. And so one participant walked again for a very long time, and so that's why we see over 3,000 walking strides in the confusion matrix on the left. The other one had a little bit of a shorter experiment before the fatigue set in. But in both cases, they had very high classification accuracy, around 98, 99%, and 100% recovery rate. And so the recoveries were, sorry, I don't know what happened there, but the recovery was essentially either due to I mentioned the backup logic earlier. So if there's a misclassification, we try to classify as early as possible to allow nice uninterrupted transitions, right? So for example, on stairs, you want to anticipate the staircase ahead of time. But if you miss it early, there's still a chance at catching it later on based on how the kinematics change, the kinematics of the user change. And so that's what we call the backup logic. And so that kicks in, and in those cases, it's still enough to complete the activity. If the backup logic doesn't catch it, then we have a way to manually, the user can manually reset the controller through hip abduction. So just they can essentially just reset it using a hip motion, and then they can recover from it. And so, as I mentioned, one of the participants did 117 laps, which is we measured it's about a 5K. So it's pretty impressive. And then eventually, he could have gone longer if we didn't add the weight to the vest. So, and so in terms of comparing to other classification approaches, we have, this is the overall, the average real-time accuracy is about 99.2%. And so it's higher than prior real-time results. Offline results, they can be very, very high, but offline results don't always translate to real-time results. Also, interleg transitions, that's what we refer to the prosthetic leading or the intact leading. I believe that we're the first to be able to demonstrate that we can do both of those based on the user's volition. We also had recoverable misclassifications. We validated the performance in an endurance setting, and in fact, we saw that accuracy actually improved over time instead of getting worse over time, which a prior study observed. And so what's interesting is that we think this improved over time because you kind of get into the zone, right? You become familiar with it over time, and part of it could be further acclimation, or just could be kind of just getting into the zone, even though there's maybe some fatigue. They understand the interpretable rules for transitions, and so they're able to become very accurate over time. And so we're also making efforts to expand our impact through releasing open source controllers, which are available for download right now on opensourceleg.com. And then we also are trying to transfer this technology to commercial products. In particular, we've been working with the OSER Power Knee, trying to transfer the SIP standard walking controller to the Power Knee. And we have an ongoing study investigating both endurance and symmetry benefits of our controller compared to both the conventional prosthesis and the OSER's stock controller. So here's a sneak preview of one of our recent participants. And so this particular experiment, as you can see, there's not much steady state behavior here, right? It's mostly transitional, non-steady behavior. And so that's really important in terms of assessing the controller, because a good number of our strides are not in steady state conditions. And then we also had a fun little demonstration that we can do other things. And I almost knocked the camera off the tripod with that. And so, so essentially here, he's using the fact that the knee angle during swing phase is synchronized to his hip angle, right? And so he's able to turn a swing phase kinematics from walking into a kicking motion. So that was kind of a neat feature that we didn't explicitly design, but it came out of the phase-based kinematic controller. All right, so changing gears. So we're also interested in partial assistance exoskeletons for broad populations. And so this can vary from individuals with full voluntary control, like people in construction jobs, assembly lines, military, munitions handling, et cetera, where you do lots of lifting, lowering, and carrying activities. It can be related to age-related immobility or musculoskeletal disorders, as well as neurological impairments. And you can see that the numbers in the USA, at least, are quite staggering. And so, in my opinion, in terms of impactful technology, if the field can figure out how to deploy generalizable partial assist exoskeletons, I feel like that will have tremendous impact because of just the broad. It's like 1 in 8 individuals, 1 in 8 adults in the United States has some sort of mobility limitation. I don't know what the stats are in Canada. Hopefully more favorable, but there's a huge need. Now, in order to design a partial assist exoskeleton, the hardware has several requirements. So lightweight, that part's pretty intuitive. Backdrivable means that the human joint can voluntarily move the exoskeleton. Essentially, they can drive the motor instead of the motor always driving them, right? So that's important because if you want to partially assist someone, they need to remain in control of their movements. They need to be able to cooperate with the exoskeleton, so both are producing forces and contributing to the gait. And so that the actuator design we'll talk about is really important, and it needs to be comfortable and generalizable. Okay, and so we'll talk about what I mean by that next. So in terms of the actuator, we're using emerging drone motors from T-Motor. This one has an integrated planetary gearbox with a 9-to-1 gear reduction, and it's extremely backdrivable. It has very, very small inertia, very little friction, which means that when you're wearing the device, even if the device is powered off, it's not really inhibiting your motion, which is really nice. So it's a very nice torque source without interfering with the voluntary motion of the user. Also cheap and lightweight, and I know that Brockoslaw is also working with similar actuators and also a similar exoskeleton design, which we call the modular backdrivable lower limb unloading exoskeleton, or MBLU. And so we have, essentially what we've done here is we took commercial knee and hip braces and we replaced the uprights and the joints with custom sheet metal parts that allow us to mount the actuator to it. And the result is these different modules. And so we've open sourced the designs, and so I know now Brockoslaw has the T-Blue exoskeleton, and we're hoping to work together some more on bringing more open source content to the field related to this. And so it's generalizable in the sense that you can use any joint configuration you'd like. So it can be hip only, knee only, or ankle only, or we can have combinations of those things. So hip, knee, ankle, etc., etc. And so the controller also really matters. So even backdrivable hardware can interfere with the user if the controller is not appropriately synchronized to them, right? And so the controller should be versatile or task adaptive. I'd argue should trajectory free, like it shouldn't be controlling position, because that's what the user should be doing, but it should be controlling torque in a way that's adapted to the activity of the user. It should be predictable and safe, especially in kind of untrained behaviors. It should be generalizable or customizable to different users and use cases. And obviously they should be effective at something, right? So whether it's reducing effort or improving performance or mitigating deficits, there should be some purpose to them. And so the approach that we've been embracing is a trajectory-free, energetically passive control method. The energetically passive part is a little bit of a misnomer in the sense that it can inject energy from step to step, but locally it's composed of passive components. And I'll talk more about that in a second. So the idea is that, imagine we can model the open loop dynamics of the human body with the exoskeleton using Euler-Lagrange's equations. If you're not familiar with this, that's okay. The idea is that we can obtain the closed loop dynamics of the system, the open loop dynamics of the system at the bottom through an energetic representation of the dynamics. So kinetic energy minus potential energy. And so once we close the feedback loop, the idea is that in this energy-based control method called energy shaping, we would end up with different closed-loop dynamics. So the idea is that we'd be augmenting the dynamics perceived by the user. Imagine if we can make you feel 20% lighter, or maybe you feel like you have, the gravity from Mars rather than Earth. That kind of thing. You could just imagine changing the perceived dynamics, the way your body moves. Those are just some examples. You could also do things like reduce the inertia contributed by your limb mass. There's some other examples, like you can add virtual springs, you can add virtual dampers. And so these things would appear in these equations of motion in closed loop, and then there would be, again, an energetic representation of it, which allows us to prove that at least locally it is energetically passive, okay? Meaning that you can't inject more energy than you've already absorbed, for example. But again, from step to step though, because we have hydrodynamics, we can still inject energy from step to step, just like changing the set point of a spring, okay? And so this energetically passive framework allows us to have, these are mechanically intuitive components, right? They're also predictable and arguably safe because they can't inject energy on their own, except for if you're actually walking. And so, and what we've taken this further is we've taken these energy shaping components, we created what we call a basis with that, and then we do data-driven optimization over that basis to match normative torques given normative kinematic and ground reaction force inputs from a multi-activity data set. And so you can see that this energy shaping framework is sufficiently descriptive to allow us to reasonably predict the human torque from the data set given the kinematic and GRF inputs. Okay. And then here we show the knee and ankle, but we've also applied this to the hip as well. And this is, again, just using instantaneous feedback from joint angles, limb angles, and ground reaction forces. And we generalize this to what we call a modular basis, modular energy basis to enable arbitrary joint configurations of the exoskeleton. So here we see an ankle, we see it's a unilateral ankle, we see bilateral hip, bilateral knee, unilateral knee. We could also do combinations of these degrees of freedom, but then there's so many possibilities that we can't show them all. And so this paper is on Tech Archive, hopefully published soon. And more recently, we've been pursuing a more customizable energy basis. So here, the basis had, I think, something like 100 possibilities that were inspired by these mechanical components, but there's so many possible parameters that it becomes cumbersome to tune it or customize it after the optimization is done. And so here we kind of boiled it down to a very small set of core functions, core components. And so these, and then we were able to then tune behavior, like for example, we were able to tune the virtual spring specifically to stair ascent, and then tune a different spring damper for non-ascent tasks, and then tune a gravity compensation function that is also task specific. And then the idea is that we then looked at, we were able to identify some task sensitive signals that would then modulate or activate these task specific functions, but in a continuous manner. So it's not classification, it's looking at a real type signal, using that signal to either suppress or activate one of these functions, okay? And so that then gives us more control over the behavior for specific activities. So then we can tune them. And you see in this app here, we're able to say, okay, we can specifically tune the amount of lift you get during stair ascent or during sit to stand and so on. And so that allowed us to, we could both optimize it using data as like a starting point, maybe like a generic control that can help the average human, or the average use case, but then we can customize it in an intuitive way for individuals or for different use cases. And this led to a study that, that was focused on fatigue mitigation for able-bodied individuals, mimicking workplace scenarios involving lifting, lowering, and carrying over multiple terrains. And so the idea here is that injuries are most common in lifting and lowering, because that's when you typically when you fatigue, especially as your quadriceps fatigue, you end up compensating using your back, and then you injure your back. That's where the injuries occur most, but that's not the only place where fatigue kicks in. So fatigue also kicks in during carrying over different terrains in particular. So you can imagine if I'm carrying an object over stairs or over ramps, that's going to be very fatiguing on my quadriceps. And then as soon as I have to put that thing down and lift up the next thing, then if I'm already fatigued, then that's where the injuries happen, is when I actually get to the lifting and lowering part. So the objective is to use a knee exoskeleton to both reduce the contributions to quadriceps fatigue, but also then to mitigate its effects when injuries are most likely, which is during lifting and lowering. And so this video demonstrates that with this controller, we were able to, well, you guess it's hard to see it just through the video, but we measured quadriceps muscle activation, and we were able to show that we were able to significantly reduce the quadriceps activation for all tasks significantly, except for level walking. Level walking was still a reduction, but it was non-significant. And this makes sense because the quadriceps knee torque is pretty minimal during level walking. But so level walking is not really where fatigue kicks in. It's during these other tasks like lifting, lowering, stair ascent, ramp ascent, that kind of thing. And so here is an easier way to see this, is just by looking at the EMG. So blue would be the EMG without an exoskeleton. Red is the EMG with an exoskeleton. Again, quadriceps EMG. And then purple or cyan is overlaying the exoskeleton torque. And so you can see that the exoskeleton torque is well aligned with the peaks of the muscle activation. And because of that, we're actually bringing down the activation peak with the exoskeleton assistance. Okay, so we're reducing contributions to quadriceps fatigue across all these activities. And then we did a lifting lowering task where we had the participants repetitively lift and lower this kettlebell, or whatever it's called, until they couldn't do it anymore, until they failed. Like they literally could not do it again while maintaining proper posture. And once they declared fatigue, then we would have them do 10 more reps and see how fast they could do it. And they could pause as long as they needed to between each rep after they declared failure. And then so the idea here is we want to see, does the exoskeleton mitigate that performance deficit after they had declared failure? So here you can see it happening. So, and the exoskeleton is off; it's passive during the fatiguing phase here. So it takes a while until they give up. Okay, so there they declare fatigue, and they say, okay, you can start again as soon as you can maintain the proper form and take as many pauses as you need. And you can see that with the exoskeleton on, there's almost very little hesitation, and they're able to just keep going. Essentially, when we see the results in the next slide, essentially we completely eliminated the performance deficit due to quadriceps fatigue. So yeah, it takes a lot longer once you're fatigued. All right, so here we can see on the left is the the bear versus exo completion time increase percent. Okay, so after fatigue, how much did the completion time increase? What is the performance deficit, right? And so you can see that with exoskeleton on, there's a very significant reduction in that completion time increase. And so you can see that they hover around 0. So it's almost like there was no performance deficit after fatigue. And here you can see this is the temporal visualization of that. So in the negative percentages here, that's the fatiguing phase of the experiment. And then this line represents the point of failure, where they declare fatigue. And this is when they did the 10 additional reps. And you can see the duration for each rep was much higher in the bear condition. In fact, we also looked at posture, or the amount of stooping, and we also found a statistically significant reduction in the post-fatigue lean deviation. And so essentially they were stooping less with the exoskeleton than without it. So again, trying to prevent these compensations that lead to injuries during lifting and lowering. And so we then, so that concludes that study. But then we started to deploy this customizable controller to different populations. So here I'm going to show a series of case studies. So this first one is with someone with frailty or age-related mobility limitations. And you can see that during stair ascent, he has to use what's called a step 2 gait. He's not strong enough or confident enough to do this, what we do is call a step through gait. But with the exoskeleton, you can see that he is able to do the step through gait, or step over gait. And unfortunately, you can't hear it because there's no audio hooked up, but at the end there, he's saying, this is simply amazing, which is really cool to hear. So we also had a case study with someone with post-polio syndrome. And so with post-polio syndrome, this individual has a severely atrophied leg, and then a relatively sound leg, although I'm sure it has overuse symptoms as well. But the idea here is we wanted to show how much of a difference having a bilateral knee exoskeleton would have over, for example, just sitting and standing. So this is what's called a 5x sit-to-stand test, which is a common clinical measure of functional ability. So you can see a pretty clear difference there. This next case study is multiple sclerosis. And so sometimes a good way to assess the value of the assistance is just to turn it off and see what happens. So here the exoskeleton is active. You know, short but pretty symmetrical steps here, right? Now we're going to turn off the controller. And so immediately you can see the participant's dragging his feet and a much slower gait, right? So, so we were able to improve knee flexion range of motion with the exoskeleton in its powered state, and essentially prevent that toe drag that is very, very common in individuals with severe MS. And so just some closing thoughts on, this is what we call task-agnostic control methods. And so essentially they're not doing explicit classification of an activity. They're essentially attempting to directly map inputs to the desired output, right, which is torque. And so, you know, I showed an end-to-end approach earlier on that was optimization-based, but there's others. There's, for example, a neural network method that was recently published in Science Robotics. And these methods can be trained to deliver, you know, very versatile assistance over many activities by just inputting a bunch of multi-activity data, kinematic inputs, then matching the controller torque outputs to the reference data, right? But these end-to-end approaches do have some limitations. You know, for example, they're difficult to tune for specific behaviors or use cases or individuals. because they're not they don't have interpretable parameters. They're also they tend to be unpredictable outside of training data, and they may require long input sequences depending on the approach. And when you have a long input sequence, like 900 milliseconds or whatever, then you're inevitably going to have some adaptation delay as you change your activity, right? And so the most recent energy shaping framework that I shared with you facilitates both data-driven training for kind of generic assistance, but then it also has interpretable parameters for customization, which we're able to use on these various use cases, right? Multiple sclerosis, frailty, post-polio syndrome, those are all very distinct patient populations. They all have their own distinct impairments or deficits. And so, but we were able to customize this one controller to all these use cases because the parameters are physically meaningful, they were intuitive. They also they have passive components, and so that makes them predictable and arguably safe as well. And it's also an instantaneous feedback control law, so it can adapt instantly as the activity changes because there's no pivot sequence involved. It's just the most recent sampled feedback from the sensors. And so stay tuned because we have ongoing clinical trials with multiple different joint configurations, and I hope to be able to share that with you in the near future. But yeah, so in closing, I want to thank all my current and former students and postdocs and collaborators as well as the funding of the National Institutes of Health and the National Science Foundation from the USA. And thank you for your time, and I'm happy to answer any questions. Yeah.
I'm curious how the bilateral knee exoskeleton handles asymmetry in the patients or the users, like in the polio case. Like, are they independent or? Yeah, so they do communicate, but they can be tuned independently. Okay. So it is useful to have them communicate. They do that wirelessly. So for example, it's nice to know when one foot is in ground contact or not. But yeah, they each have their own basis functions that can be independently tuned. Cool.
Yeah.
I was also wondering about the weight of the foam, like above knee prosthetic. I mean, if there's like extra work exerted on that side of the patient's body because it is heavy, or not? It is heavy.
At least not the power is very nice and very light. You probably notice the difference there. It's a very slim device, right? But yeah, our experimental hardware, the two degrees of freedom, it's pretty heavy. It's I think something like 11 pounds or maybe between 5 and 6 kilograms. And the goal is to get that as light as possible. So you particularly feel that when you're standing still lifting up the leg, because it's all just mass you're pulling up, right? But when you're walking, at least, the participants say they don't really feel the mass as much because it's propelling itself, right? So it is actively helping during walking. But yeah, if you're just standing around shuffling or if you're around, then you just feel the weight. And so we really got to bring down the mass. But the Oser Power Knee, although it doesn't have an actuated ankle, it's quite lightweight. It's very nice.
Cool. Thank you.
Yeah, great talk. It was fascinating. I was wondering how much would additional environmental sensing help you guys in the controller? So I'm kind of thinking like how the human brain works. Like, I already thought of it, but I was kind of thinking about a trigger talk. Like, the way I'll stand up from a chair really depends. Like, this one has footholds on, or that, how I behave when I walk in a crowd will depend on how crowded, how dense it is.
Yeah.
People. So I was wondering, like, if you had more sensing, like, maybe like camera images. Maybe also telling you something a bit more about the environment, more than what you or trusting sensors.
Yeah. If we had additional features, and Brocklesaw's certainly working on that. I'm sure he has something to add here, but we would definitely use additional features if we had them, and we're trying to. But we're very careful about not adding those features at the cost of like power consumption or adding more weight or bulk, that kind of thing. So we are exploring other options. So our latest iPhones have LiDAR, and it's a pretty cheap, lightweight sensor, right? And so we're thinking about maybe trying one of those more recent consumer LiDAR sensors they're as small as the ultrasonic sensor, and they're very comparable in terms of power consumption and weight and cost, but then they have their own unique drawbacks like sensitivity to light conditions and stuff like that. But anyway, any sensing modality has its drawbacks. So yes, we are definitely interested in adding features. So for example, being able to estimate step height would be very valuable, especially before you hit the staircase. And LiDAR might be able to help us with that. Yeah, cameras, of course, are also, you can get a lot of information out of cameras. Then there's also computational overhead and stuff like that. So and latency is also something that we have to consider. But there may be ways to work around these things. And so, we could talk more with Bratislava afterwards, but I'm sure he has thoughts on this.
Actually, I was about to ask how you guys get a stair height. Is it like a pre-assumption tool?
Yeah, so currently we are preloading the step height.
Right.
Yeah, so right now we don't have any way to adapt to it, but we're working on that. So either through LiDAR to measure that feature or dead reckoning through the foot IMU.
Right. And for the transition model, let's say from the flat ground to the stairs, I can imagine using ultrasonic can detect the distance and change the walking gait. But how would you do that for the incline down?
Yeah, you're right. So it only helps with the stairs ascent. Yeah.
So you have to manually activate the transition?
So we have a little bit of a trick there where, so what we do is we have a kind of a two-phase process to do the walk. So you're talking about the walking to stair descent transition, which is the hard one.
Yeah.
So what happens is they slow down as they're approaching the stairs, and as they slow down close to a stop, the classifier will switch to the sit-stand mode. It turns out that the sit-stand controller can actually do the stance phase of stair descent. If you think about it, when I'm sitting down, it's almost like lowering myself down the stairs, right? And so what we do is we switch to sit-stand mode at the top of the staircase, and then as you begin descending down the step, it will recognize, okay, these kinematics are different than sit to stand. So we're going to then switch to stair descent. So there is a two-stage or two-phase process, but it can happen very quickly though. Like as you saw in the videos, like they weren't really stopping, so to speak. They were slowing down, yes, but that's also very common when you approach a stair descent. You want to be careful with foot placement and everything, right? So, but yeah, that is one of the harder transitions, and so we do have this little.
Nice. That's a nice trick.
We just kind of serendipitously discovered that, like sit-stand controller works for the stance phase of stair descent. Doesn't work for the swing phase, but we can figure out that we're in stair descent by the time we get there. So.
And you mentioned slowing down. Would you have to change the walking gait of your controller for the background?
When they're slowing down.
When you're slowing down,
So.
It just totally depends on the theta.
Exactly. Yeah. The phase variable synchronizes the speed, but also we can detect walking speed and modify the desired kinematics or impedance as well. We have two ways to do that.
So you mentioned that, first of all, great talk.
Oh, thank you.
Really interesting, but for the prosthetic controller, you switch to just a position mode controller instead of an impedance controller when you're doing the walking phase?
During swing phase.
During the swing phase.
During swing phase, yeah.
So that's just when you don't have any contact?
Yep. During all the stance phases, we're using the impedance controller.
Oh, okay. So that's when you're walking, you're still entering stance phases.
Mm-hmm.
And while you're in the stance phase, you're okay.
Yep.
That was okay. That answers my question. Thanks.
Sure.
Thank you again for the talk. Just maybe a high-level question around control paradigms. I'm wondering why you went down the continuous time route and what drew you down there, and something that seems to constantly throw you back into like a discrete control paradigm. Are you happy with that decision? Are you sitting there there are whole paradigms too for thinking in discrete time and how you might do control that way. I'm just wondering where you're.
It's a very fair question. And so if I was to, I may have ruined my screen share here, but at least the people in person can see. I'm trying to go back to, there we go. Right, trying to go back to that slide. But so the idea, we want to get rid of the discrete all the discretizations because of the complexity. That's one reason. So these continuous controllers tend to be more subject independent. So granted, they're optimized for the average person, which is not any one person, right? But that's good enough to start and good enough to walk pretty comfortably. And so we found that these continuous controllers are more subject independent, whereas the discrete ones, they require a lot of subject-specific tuning. That's one reason. But you also asked, why did we find ourselves coming back to like this finite state machine here? And so we had an approach before this that used essentially, you can imagine the y-axis here being thigh angle, and then the x-axis being thigh velocity or thigh integral. And if you're walking in a rhythmic, consistent manner, that forms then an orbit. And you can use atan2 and you can get the phase angle of that orbit, right? We tried that, and that worked really well for steady state walking. It was horrible for non-steady state walking, because then you lose the nice circle, the circular property. You may get self-intersections, you may get all sorts of behaviors that cause trouble. And so we decided that we really wanted to have what we call a holonomic representation, or something that's purely based on angles and not velocities. And so that's how we came up with this. But then you need to have structure to separate out these piecewise monotonic regions, right? And so I found that adding the structure is we've been able to do it in a way where it provides predictability. For example, it makes sure that we don't transition at the wrong time to the wrong mode or whatever. Sorry, the wrong mapping, not mode, mapping from the piecewise monotonic trajectories. And so that structure is helpful in terms of robustness, predictability, that kind of thing. But with a small sacrifice in complexity, right? Thankfully, none of this has patient-specific parameters in it. Like we don't tune this to individuals. So at least we're able to avoid that drawback of the additional complexity.
And like the tuning conversation, is that maybe why, like my sort of next question was why you chose hip angle versus, like I've seen hip position as well as the phase variable.
Yeah.
But then you would need to have knowledge of the model of whoever's working. Like would that be your main?
Yeah, so you're talking about like Cartesian hip position?
Yeah.
Yeah, so that works well for like autonomous biped robots when you have measurements over both legs.
Right. Yeah.
But then for a prosthetic leg, you don't have that, right? And so, so unfortunately, you can't really get, first of all, very accurate measurement of Cartesian hip position, because you'd have to use dead reckoning to do that during swing phase. There's challenges with dead reckoning, and also we wanted to give the user something like they can directly control. And what better way to give them control over the robot than their own hip, right? Of course, the downside is then this doesn't necessarily work with hip disarticulation patients. So if they don't have control of their hips, then they don't have control of the phase variable, and I think this whole paradigm may fall apart. We actually are going to try it, maybe even next week. I think we have a hip disartic participant coming in to try to see what happens, but I'm not confident because there's no way for them to control the input other than maybe they could through kind of ballistically control the phase variable, but I don't know. We'll see what happens.
I have one other follow-up question. In terms of like this paradigm again of maybe imposing normative findings on prosthetic patients, or
right.
like is there anything stopping you from going a different way of saying, even going from like an adaptive or like a reinforcement approach and saying go nuts with whatever you can do with this knee, and like allowing someone to maybe like augment their gait in a completely different way that's not normative? Is there anything stopping you?
We're actually working on that. I think the average able-bodied data is I think a good starting point. You need an initial model for the RO, right? Because you can't like unless you have some sort of great sim to real pipeline, you can't run 1,000 experiments, people falling over and stuff, right? Like that's not practical. So we start with the initial model from able-bodied data, and then yes, I think reinforcement learning has a lot of potential there. There's some good work being done in Helen Huang's group at NC State University. They've already started using RL for, I think, tuning more FSM style controllers, finite state machine controllers, but maybe doing continuous controllers too. I can't remember exactly what the latest stuff is, but yes, I think there's definitely potential for that. We're looking at that. Yeah, yeah, personalization is really key. And we get this question a lot about like whether it's even appropriate to use able-bodied data in the first place, because muscle anatomy has changed because of the amputation. There's also not a rigid connection between the prosthetic leg and the skeleton, right? There's soft tissue interaction there, and those are all good arguments. My response to that is still I feel like the able-bodied data is a great starting point for restoring normative gait, and from there we can then do these personalizations or tuning, tweaking, as long as the controller is interpretable, to make it even more appropriate, right? And to accommodate the subtle differences that will always be there, right? But yeah, the idea is that if we can get at least close to able-bodied gait biomechanics, that will at least reduce, probably not eliminate, but reduce some of the compensations with the intact joints and minimize the overuse. Yeah.
Yeah, good talk. I was curious about the power consumption of these. So I guess approximately how long, at least with the ones you're working on right now, how long can these last before they need a recharge? And have you found any of the factors of the control or maybe the task, does that affect the power consumption, or is it more dependent on the person using it and their base level of strength that they already have?
I think it's all those things, like the weight of the user, what they're doing, all those things definitely matter. I can just say on that multi-activity circuit that I showed you in the endurance study, the typical battery, which is a pretty lightweight battery that we use, that can last about an hour. Because there's a lot of sit-to-stands and stairs and ramps. Those are very power-hungry activities. We do have regenerative braking, like when the actuator is doing negative work, they are actually charging the battery, but it's not perfectly efficient, right? I mean, maybe we capture like 50% of that energy back, but we're still losing 50% during negative work. And so yeah, an hour is not great, but that's pretty intense. That's a pretty intense hour of activity, which is not really representative of daily life, right? But what we did do is we added a larger battery for the endurance study, and now we can go like 4 hours uninterrupted. Not that anyone wants to do that, but we can. And so, but when we did that, we had to move the battery off the leg onto the back, because you don't want to have the kind of mass on the leg itself. And so, as long as you're willing to move the battery off the leg and put it onto like a belt or something, then we can increase the battery and the longevity of the device, no problem. That's with our 2 joints. The Oster Power Knee can last longer. It only has 1 joint, and the knee also doesn't do positive work during walking. It does during stair ascent and sit to stand. But so then I think the Oster Power Knee is less power hungry. It also doesn't have as much torque as well, so that also contributes to using less power. So the Oster Power Knee can last a lot longer. Yeah. Okay. Yeah.
Thank you for your excellent talk. I have a lot of questions.
Sure.
I'll have a chance to ask them here.
Yeah.
In your transitions, have you considered like quick directional transitions, like pivoting?
Oh, pivoting. Yeah. So we do. I definitely didn't mention it, but we do have like a turning state or mode, and the only purpose of that is to prevent it from going into like. To prevent it from going into stair ascent accidentally, right? So I can imagine if I'm turning around, the ultrasonic sensor might see an object and think it's a staircase.
Yes.
We don't want that happening, right? So we disable certain transitions when we recognize turning. We use the IMU for that. We don't need to change the controller to do turning is because we don't have out-of-plane actuators anyway, and the sit-stand controller is pretty robust to turning motions. So yeah, we do recognize it, but for the purpose of preventing misclassifications, we don't recognize it for the purpose of enacting a specific controller. But I do think there's potential there. Yeah, we just have not looked at that. Yeah, we've certainly found that like the semicircle turn, the walking controller seems to work fine. But yeah, those sharp turns, we just go to the standing controller and then yeah, and then they can do it. Mm-hmm.
Any questions on it?
No, there's no. Oh. Yeah.
Okay, so it's just this one right
Yep.
here. So I'm wondering what's the main factor or strategy to achieve a significant accuracy improvement from 85 to 99%? That seems amazing.
So, yeah, okay. So I think it has to do with the simplicity of the activity space primarily. So when you're having to differentiate between ramps and walking, that's where you're going to get a lot of classification errors because gait during ramp ascent and ramp descent looks very similar to walking gait on level ground. So I think merging those activities into one classification mode, I think contributed substantially to reducing classification errors. And then also because you don't have to differentiate very subtle differences, we're able to use fewer rules, more interpretable rules and trainable rules, so we can actually tell people how to walk when they want to transition from one mode to another. So for example, I don't know if you noticed in any of those videos, when they're doing stair descent to walk, we tell them to kick out their leg in a kind of an exaggerated manner, and then that triggers the walking transition. And so that's a very trainable thing. And so, yeah, so I think the participants, are able to learn, they're able to interpret these rules, and then therefore make subtle changes to how they use the device to have high accuracy. Of course, the goal is that those changes aren't detrimental. Hopefully they're not, but we haven't analyzed things like metabolic cost or anything like that yet. But we did again look at endurance, and we as you can see from the results, at least one person was able to do a really impressive number of laps. So at least for that participant, they weren't held back by these subtle things that they learned to do to trigger the transitions.
All right, well, thank you very much for coming and for the talk. So let's everyone do a round of applause. And we have some time afterwards, so if anyone wants to stick around and ask some more questions and discuss some cool robotics, we have time for that, and then we'll go from there. All right, thank you everyone.
Yep. Sign up now.